Okay, since our unit is predominantly going to concentrate on cubics and quartics, those are going to be the two kinds of graphs that we talk about, and you guys are going to begin analyzing them. And when you have a cubic function, typically we refer to it as like an S shape to the graph. What it means when it says the curve rises from left to right if a is greater than 0. So here's an example of what it looks like when a is greater than 0. Remember that a is your leading coefficient. And when your leading coefficient is bigger than 0, then it controls the right end of the graph. And it makes the right end go up towards infinity. So we've got two ways of writing that notation because we're going to be asking you for the end behavior of these graphs. So if I ask you for the right end behavior of a positive cubic function, as soon as you know that the leading coefficient is positive, you know that the right end behavior is going to go up. So you have two ways of saying that. You say that as x approaches infinity, because that tells me you're going right, and then you also tell me that y approaches infinity, because you're saying that as you go right, you go up forever. But remember, we also introduced you to a notation last semester called limit notation, and we used it really recently, just in the last unit we did end behavior. So we could also write the limit notation that says that as x approaches infinity, our y value approaches infinity. If we ask you to explain how you know that, or why that is, then what you would say is you would say that your a value is greater than 0. Okay? Now, the reason that the left end goes down is not because of the right end. It's because of the degree. This degree, when it's a cubic, is an odd number. And when your degree is odd, that tells you that your ends go in opposite directions. So what you want to do is you want to identify what the right end is doing first. And then you can say, okay, well, now that I know what the right end is doing, I can look at the degree. And if the degree is odd, the left end will do the opposite of what the right end is doing. Okay? So then it becomes, well, how would I explain the left end behavior of this graph? So you would have your two options. One option would say that as x approaches negative infinity, so that means that we're going left. And as we go left, our y values also approach negative infinity. So we're saying that as we go left, we go down forever. In limit notation, that would say the limit as x approaches negative infinity, because we're still saying that we're going left, and the limit is y is approaching negative infinity as well. So you have those two options as to how you write it. And then, if we ask you to defend it, if we ask you to explain how you know what that is, then what you would say is you would say, because the right end behavior is positive and the degree is odd. Okay? If your leading coefficient is less than 0, so that's what you see right here, then remember the leading coefficient controls your right end. So when a is less than 0, that makes the right end go down. Once you've determined what the right end is doing, this still has an odd degree. So this one would have an a value that was less than 0, but it would still have an odd degree. So once you've determined that the right end is going down, then that proves that the left end has to be going up. That's what gives it that S shape to the graph. So if I asked you to explain the right end behavior of this graph, then what you would say is you would say as x approaches infinity, because you're still going right. But this time, as you do that, your y values are going down towards negative infinity. So the limit notation would say the limit as x approaches infinity of y is negative infinity. And if I asked you to defend that and explain that, you would say it's because of that, because your leading coefficient was less than 0. And then if I asked you to explain or describe the left end behavior, you would say as x approaches negative infinity because you're going left, y approaches positive infinity because you're going up. And in limit notation, you would say the same thing. You would say the limit as x approaches negative infinity of y is positive infinity. And then once again, the defense of that, or the explanation of that, would include both of these, because this is saying I've already figured out what the right end is doing, and this is saying that the left end will go in the opposite direction. When you have a quartic function, quartics look like a kind of a bubbly looking W when they're positive, and they look like an M when they're negative. So the reason that it has that W or M look is because the right end is still controlled by the leading coefficient. So you see here A is greater than 0, so our right end is going up again. But what has changed this time is that our degree is even. It's an even number. And an even degree means that the ends go in the same direction. So once again, you always want to do the right end first, and you look at the leading coefficient. This one right here has a leading coefficient that's positive, so the right end goes up. And so the right end behavior, you would say, you know, if I wanted to write it as more of like a sentence, I would say since A is greater than 0, the limit as x approaches infinity of y is infinity. So I'm saying that since my leading coefficient is positive, my right end behavior is heading up towards infinity. And then for the left end behavior, you would say, oops, can't spell, since A is greater than 0 and the degree is even, so that tells me since my right end is going up and my degree is even, then the limit as x approaches negative infinity, because now I'm going left, but y is still approaching positive infinity. So I want you guys to try writing out the explanation and the notation for the end behavior of this negative quartic over here. So go ahead and just pause for just a second and give that a shot. Okay, so this should be what you have. You would say my leading coefficient was less than 0. So as x went to infinity, y went to negative infinity. That's the right end behavior. And then since my leading coefficient is negative and my degree is even, then my left end behavior also goes to negative infinity. Okay, so it's just using our old notation to describe new kinds of graphs. The way that we're going to use this is we're mostly going to use this to check ourselves and make sure that the equations we're writing make sense. So if I look at this graph right here, I see that the right end is going down, and I see that the left end is going up. So I know I'm going to have an odd degree, and I know that my leading coefficient is going to be less than 0. And I should confirm that as I work through this whole process. Okay, I also know that my odd degree in specific is going to be a degree of 3, and I know that because of the x-intercepts. So that's why we did the notes on zeros and multiplicities. So there I see my graph go straight across the x-axis at -2. And so that tells me that that solution only occurs one time because it goes straight across the axis there. Okay, but at this x-intercept, at x equals 1, I see my graph bounce there, and that tells me that my multiplicity is going to be 2. It's going to occur twice because that's what causes the bounce. Okay, and then if you look at step 3, it says that we're going to need to determine a specific a value now. And that's why you see these little dots right here. I'm drawing anchor lines to a specific point on the graph right there. And that specific point was -1, -2. And so we're going to use that specific point to find a specific a value. Okay, so we're going to start our process. We're going to combine what we did on our review quadratic notes and what we did on our zeros and multiplicities notes. And so what we're going to do is this. So choose a different, darker color. Okay, so I have x equals -2 as a single solution, and I have x equals 1 occurring twice as a solution. So I start my intercept form. I don't know what a is. I can't just decide it's going to be 1 this time. I'm going to have a specific a value. Think about it. If I just got to choose a was 1, the right end of my graph would go up. Okay? And then because of these three roots right here, I'm going to have x plus 2, x minus 1, and x minus 1 as my factors. Okay, so step 1 is to make sure you know how many roots and what they are, that kind of thing. Step 2 is to put them in your intercept form. Step 3 is to find your a value. And so I'm going to plug in this x right here and this y right here, and I'm going to solve for a. So I plug in the -2 for the y, and I plug in -1 everywhere I see an x. Okay, so I have -2 is equal to a times, this right here is just 1, this is -2, and this is -2. So I have -2 is equal to 4 times a, and that makes a -1/2. Okay, and then the fourth and final step is to multiply it out into standard form. So I have my specific a value, and I have my factors. And I can multiply in any order. Really doesn't matter what order you go in. I'm going to go ahead this time and I'm going to do the x minus 1 and square it. And so I would get x squared minus 2x plus 1. And then I would go ahead and I would take that x plus 2 and multiply it through. And remember, we've talked about all the different ways you can do that. You can do the kind of Punnett square multiplication process. You can do that vertical long multiplication process that I like to do, or you can just use your distributive property. So I want you to take a second and pause the video and make sure that when you come back on you get the correct cubic before a got distributed. So just your multiplication answer. Okay, what you should have gotten when you did your multiplication is you should have gotten x cubed minus 3x plus 2. And then our last step is to distribute that -1/2 through there. One of the most common mistakes, I'm going to jump off here to the top for just a sec. One of the most common mistakes is that people want to write it like this. They drop the parentheses before they distribute through. And that's not correct. This entire -1/2 was being multiplied to the entire cubic from your 3 factors. So you need to make sure that it distributes through, because if you forget those parentheses, you've got 2 of the 3 terms of your cubic wrong. Okay, so when we distribute that -1/2 through there, our final answer should be -1/2 x cubed plus 3/2 x minus 1. And another thing that we can use to check this, usually, not always, it doesn't always show up nice and pretty on the graph, that constant at the end of the equation should agree with our y-intercept, which ours does. Okay? And our leading coefficient agrees with our right end going down, and the degree of our equation agrees with the left end going in the opposite direction. Okay, so those are all the things that begin to tie together. So, once again, we're going to just do one final example. I want you to take a second and I want you to just brainstorm. What are all the things you know about this graph before you actually begin the algebra process of multiplying it out? So take a second and just begin thinking about that. Okay, so hopefully some of the things you're thinking about, are you thinking about your right end is going up, so you know your leading coefficient is greater than 0. The left end is also going in the same direction, so you know that your degree is even. And then if you look at your x-intercepts, you have one where you go straight across, a second where you go straight across, a third where you go straight across, and a fourth where you go straight across. And so that means you have 4 separate and distinct solutions that each only occur one time. So that proves you've got a degree of 4, which just confirmed that it's even. Okay, so we're going to go ahead. We're going to set this up. Got y equals. Our first solution was x equals -3. And so our first factor would be x plus 3. Our second solution was x equals -1. So then we have x plus 1. Then we have a solution at x equals 0. And so that just gives us an x. And then finally, x equals 1, so x minus 1. Okay? And then we need to find our specific a value before we can actually multiply out. So here's my anchors down to this point right here. And that point this time around was the point -2, -4. So we plug -4 in, and then we plug -2. Okay, so pause it for just a second and let's make sure you can find your a value correctly for yourself. Okay, hopefully you got an a value of 2/3. If not, you just need to go back and check your arithmetic. And so what that means is we have y equals 2/3. I'm going to just rearrange my factors a little bit. You don't have to do this. I'm just doing it, and you'll see why in just a sec. Okay, so you see how I'm doing just a little bit of rearranging. And the reason I did that is because now I don't have to do any long multiplication. When I multiply those two together, there's no foiling needed. It's just x squared plus 3x. And when I FOIL those two together, they're conjugates of each other, and it just becomes x squared minus 1. So when I multiply the final time, it's still just foiling. And so what I should get is y equals 2/3. And when I FOIL all this out, I get x to the 4th plus 3x cubed minus x squared minus 3x. Okay, and then don't forget, make sure that you put parentheses right here and here so that the 2/3 isn't just attached to the x to the 4th. Because you need to make sure to distribute through the whole parentheses. And so y equals 2/3 x to the 4th plus 2x cubed minus 2/3 x squared minus 2x is your final answer. And unfortunately, whenever your y-intercept is 0, you can't use your y-intercept to calculate a, you can't use your y-intercept to make sure you did your multiplication correctly. I mean, anything could have made your y-intercept 0. So it's not as handy as the previous graph. So that's it for today. And then don't forget that you have a quiz on Intro to Polynomials coming up.